multiply these two things, you can easily see that you get the identity. So hence this is a unitary operation. And think of the calcite crystal in the beginning of my experiment as the Hadamard transform. We will see later why, but I want to make that link. We'll see now. So let's play with the Hadamard. So remember we had this qubit that was in a superposition of 0 plus 1, each with equal amplitude. Well, when you apply a Hadamard operation to that, then let's do well, when you do the calculation, you will see that you get 1/2 plus 1/2. Like this is 1/2 plus 1/2 is 1. And here in the lower one you get 1/2 minus 1/2. And actually here is what comes back, this interference, and these two things cancel. And actually here they add, and you get the 0. So when you apply a Hadamard transform to the 0 plus 1, you will get a 0 back. And because it is its own inverse, as we saw, if you apply a Hadamard to the 0, you get this superposition of 0 plus 1. And again, think of this calcite crystal as doing exactly that. You had this 45-degree polarization photon going in, and then the calcite crystal split it in an equal superposition of being in the upper tract and the lower tract, which if we could call the upper tract 1 and the lower tract 0, then this is what the Hadamard does. Equally, you can compute what it does on the state 1 over square root of 2 minus 1 over square root of 2, which seems to be the same thing, right? Because if you measured it, this state, you will still get with probability 1/2 0, and with probability 1/2 1 if you measure this state. Because minus 1 over square root of 2 squared will still give you 1/2. But nevertheless, when you apply Hadamard to it, you will get the 1. And again, applying a Hadamard to this thing will give you a 0 minus 1. Oh, and another way, of course, of thinking about these unitary operations is just that they are a change of basis. They map basis states into another basis. Oh yeah, and what I want to say is that really the important thing for computation is not that these numbers they actually aren't, but that these numbers are complex or even real, but that they are negative. Sort of, you sometimes hear about that you have negative probabilities, which doesn't really make sense, but the property that these amplitudes can be negative and cancel with each other, that makes what the thing that makes it interesting and different from probabilistic computation. Okay. So if you apply Hadamard to n qubits, so note here that I just did the n-fold tensor product of the Hadamard, which physically you can think of, do a Hadamard to your first qubit, do a Hadamard to your second qubit, independently do a Hadamard to your third qubit. If you have an n-bit state here, and you apply a Hadamard exercise, if you want to do exercises, then you will get this state, which is an equal superposition of all the possible 2 to the n bit states, and you will have amplitude in front of your register of minus 1 to the x dot y, where here I just think of inner product modulo 2. To concur, if we have all zeros in our n registers and we apply a Hadamard, we will get an equal superposition of 1 over square root of 2 to the n, and then each 2 to the n bit add 2 to the this shouldn't actually, this should be an n here. Excuse me, this m should be an n. All the 2 to the n bit strings basis states occur. And note that this minus 1 to the x dot I will always be 1, because 0 dot something is 0. Okay, and note that if we had just 1 0, this coincides with the superposition of just 0 and 1. That is all the 1 bit states. Okay, another important thing of qubits is that you cannot copy them. So, unlike sheep, I guess Dolly was the first one that was cloned, you cannot clone qubits. This is an old result of Wouters and Zurich, and actually of a Dutch guy, Dix, from Utrecht. And this is not good, but give the whole proof without these pointers. So the proof is simple, and this just gives you a nice idea of how these things go. Suppose that I had a quantum cloner.
What mathematically is this?
Okay, let's examine what that should mean. It means that I have a unitary operation, which I define here as the U for clone. And what it should do is, I give you 2 qubits, a clean qubit put in the 0 state, and an arbitrary qubit in alpha 0 and beta 1.
One should be in cat.
Yeah, one should be in cat. Mistake here. Then what it should give me, 2 copies of the qubit. It should give me alpha 0 plus beta 1, tensor alpha 0 plus beta 1. That's what I mean, what a cloner should be. Okay? I have 1 qubit, and I have to supply, it has to be a unitary thing, so I have to give you a clean other register 0, and then after, when I do the operation, at least when I put a 0 there, the unitary should give me 2 copies of the original qubit. By the way, I also should specify what it does on the 1 here, in order to fully specify the unitary, but I know I can specify something there. So I just have specified it. Okay, so I get this 2 copies of this qubit, which if you just use the calculus of tensor products, can rewrite as alpha 0 0 plus alpha beta 0 1 plus beta alpha 1 0 plus beta beta 1 1. Okay, so that's one. This state is equivalent to the 2 copies. There's nothing happened here. That's just mathematical rewriting. But now let's look differently at it. Let's look at alpha 0 plus beta 1 again. It should be cat 1 tensor 0, and let's rewrite this thing in between here, which is equivalent to alpha 0 0 plus beta 1 0.
Yeah, but sorry, can you say again?
Yeah.
So the unitary operator UC is a cloning operator.
Yeah.
If what?
If
something is definition here, probably.
I'm giving two things. I'm giving what it should do is okay. If you want the definition, you have a qubit A, and you have a clean qubit B, which is 0.
Yeah.
And what I want is that what the cloner does, it takes qubit 1 and puts it at the place of qubit 2.
Yeah, so the diagonal side
that is this
just definition of clone.
Yeah.
And all other things are explanation why it is possible. Yeah.
Yeah. Well, and I will actually also look. So the unit. Yeah.
Yeah.
Well, this is what it should do. But also I can rewrite the state here as the state alpha 0 0 plus beta 1 0.
Yeah, but it's just not
it's the same
because
state.
of the cloner, just because.
No, that is just because that is the equivalent way.
Yeah.
And now, because a clone, this is a unitary operation, it's a linear operation. I can split this thing and saying what the cloner does on this superposition is what the cloner does on this thing plus what it does on this thing. Okay? But these things now are classical things. Right? So in particular, what the cloner should do, if I give the first qubit the classical 0, then it should give me back 0 0. Right? Cloning a 0 in a 0 state. It gives me 0 0.
Okay, just you substitute alpha is 0 and beta is 1 to the first line. Yeah. What you do really.
Yes.
You apply the definition of
I apply what a cloner is to this particular
special case when alpha is 0 and beta is
yes. And also I do the same thing here when alpha is I guess 0 and beta is 1. Okay, here alpha is 1.
Yeah.
Well, this is yeah.
But do you understand it right that formally you should first take alpha and beta out of the new that you see?
Yes.
And then you get the qubit.
Yes.
Because before that you don't have a qubit.
Yeah.
Okay.
We'll still bit more if you allow auxiliary qubits and you're allowed to leave any garbage in them after the cloning.
Any garbage?
No, but it seems that just...
Well, but then we have to, then I have to actually go into density matrix formalism to talk about what this thing is.
It's okay.
For you it's okay, but I haven't...
No, but that is...
Whose answer? Yes or no?
No, it should, it's impossible.
No, but it seems...
Not possible, even...
Sasha, this transformation is non-linear.
Yeah, just what...
Any transformations with density matrix is also linear.
Yeah, but Sasha's question is, what if I allow myself more junk, more memory to do a more complicated computation and then ignore?
It will still be the case.
No, it's a bit strange, but what you say is that this alpha square on the right side is not linear in alpha.
Alpha square.
Yeah, you have alpha square, this coefficient.
Yeah.
It's not linear in alpha. So it cannot be more or less. So it's
One
strange.
quadratic form can be equal to linear.
Yeah.
Even on, so it's a bit strange that you need 3 guys to find this.
3 guys.
On the previous you probably know this earlier, no? If somebody asks.
It's interesting, but I don't think these physicists really
understand what is alpha square.
Well, look. In a way, there's sort of another physical way. I mean, you may have heard of Heisenberg's uncertainty principle, which says that in particular it says that if you have a superposition, then you cannot know alpha and beta arbitrarily precise.
Yeah.
Now, suppose that you could clone, right? You could clone your qubit, and you could make 1,000,000 exact copies of it, and then you measure them, and then you look at the probability that you get out, you get a very good estimate of what alpha and beta are. And if you're not happy with that, you clone a couple more and you do more experiments.
You are the knowledge of outbreak.
So I guess they knew. But the precise one is given by these 3. I mean, there's question about how well can you clone, for example. I don't want to do it exactly, but I want to have 2 copies which are close to